scan statistics.
Great. So thank you for inviting me and for all the talks in this workshop so far. So I'll talk about something which I think is the most different from any other other talk in the entire workshop. So it's still on for big data techniques. I'm using Coresets instead of sketches. It is going to be sublinear algorithms, but this and I should say this work is mainly with my PhD students, so Michael Matheny, but this talk will be in the intersection of sublinear algorithms, so it fits in the theme of the workshop, and also statistics, and also in computational geometry. So some of a lot of the nearest neighbors stuff is computational geometry problem, but this will be more low-dimensional computational geometry. So I hope that's okay with everyone. I won't go through most of those parts of the details. Mainly we can do proof by pictures if we need to. It's a nice thing about low-dimensional geometry. So let's see. So the big theme often in sublinear algorithms is you've got some big data, some big N. You want to do some sort of analysis on this, and you're happy if you can get an answer. But often this is maybe it's a polynomial and N is the analysis. So what you might want to do instead is do a sketch or a coreset of the data, which is going to be a much smaller set that is going to retain some of the properties. If you haven't heard of a coreset instead of a sketch, it's essentially something more restrictive, where the data set looks like it's the full data. The data points have, say, the same dimensions, same properties. It's just smaller, and you want it to maintain the rough properties of the full data. Now, when the data is much smaller, you can run the same analysis on it. Now it's polynomial in S instead, and you're happy. Okay, so this will be the kind of the big kind of approach we're going to take, and I'll show that I'll fill in more of this picture because there are more challenges in here. I've kind of I've skipped over at this point. But so in particular, we're going to be talking about large spatial data. So a lot of data we've seen generated in this talk is from like the internet or machine learning, and you often represent these high dimensional features. This is also, I'd say, not as dramatically, but we've gotten a lot of big spatial data as well. This is often in 2 dimensions or some low dimensions space. These are 70,000 crimes from Philadelphia. These are 60,000 hospital patients near Pittsburgh. So 1 million geolocated tweets a day. I'm working with some people who are capturing these. This is a really massive data set. There's 100 million of like just credit card transactions a day, and these are geolocated. So understanding the spatial properties of these is kind of, and sometimes an important issue. And also, we don't often just have the raw data and just look at the density. Sometimes I look at those problems, but I'm interested now that certain of them are special mark points, where they have a value. You can either think of they have a binary value on top of them, and the ones are interesting, or they have a continuous value on top of these. I want to know something about this measured quantity on top of the spatial data. So there's spatial structure. That I don't want to get in the way of understanding this measured property. Where does it spatially aggregate? But I don't want to know, say, okay, the data is dense here around a city, but I want to know if the measured data is dense relative to the background population. Okay, and yeah, so that's what I just said. So there's kind of been from about 20 years ago now, there was invented, essentially was now established as the right way to look for these anomalies in this measured data on top of spatial data, which is called a spatial scan statistic, introduced by Martin Kulldorff in 1997. And you want to find where the measured data is significantly denser than the background data. And so to do this properly, you need to actually, and not all people applying this necessarily follow this, but I really believe you need to add some geometric structure on here, and you want to determine some family of ranges and find the object inside the class of all disks, all axis-line rectangles, which given this measured data set, then there's some statistic, and you want to maximize the statistic over all possible of these ranges. Okay, and so typically what's looked at is you define some null hypothesis and some H1 hypothesis that there's something kind of significant happening here, and you can write down some function which happens to be some log likelihood ratio, and this is what you optimize. But I'll explain why, for our purposes, we won't really need to worry about what this is too much. Okay, and then the task, the computational task, is to scan over all of these classes of regions. So I need to consider, in order to figure this out, which region maximizes the statistic. You know, I almost need to check every single one of these regions, right? So I have to. So that's for the scanning part of the scan statistic. Okay, and so this is a computational issue. This is a polynomial time algorithm. Basically, that is slow, and we'll see this causes issues.
So, I mean, when I look at the problem this way, I mean, it looks very much like, you know, you have a class of very low visit dimension, the class of all disks or the class of all half spaces. So a very small sample can give you a uniform approximation to the weight of all the sets. And
yeah, so we'll see. Yep. Yeah. So I'll show you this first thing to try, and this doesn't work as well as you'd like, because this ends up being a big polynomial, or not huge, but big enough that it's uncomfortable with the sample sizes you need. Okay. So I'll show you some plots. Yeah. And then on top of this, you actually you found the region which maximizes some function, but you don't know whether this is actually significant or not. So typically the standard practice is you re-randomize where the measured values are, and you rerun this 1,000 times to check against that distribution you built. So not only do I have to search this polynomial set on a big N, but I then need to do it 1,000 times. So it becomes kind of a painful operation to do.
So what does it mean random data?
What?
What does it mean random data? Random subset of the data?
Well, right now I'm running on the full data, and this is what most people do in practice. So okay. And then we'll get to random subsets and other things you can do.
So it's random subset. It's not like a random genetic.
No. I mean, I've only drawn 100 points here, but these are from, typically people run them on these much bigger data, or would like to run them on the much bigger data sets with thousands or millions of points, which until this they weren't able to do.
I think the question was about the random data. I think that's part of the permutation test.
The permutation test, I'm not changing the spatial location of the data set. I'm changing where the measured values are. Think of if there's a subset of 10% of the points are red, and I want to say the density of the red points is higher than the full distribution, I will randomly perturb where the red points are.
Or perturb them.
Yeah, I will change the label. I'll say this point's red instead of this point. Right? I will randomly assign a subset of 10% of the points to be red, rerun the algorithm, and I get some range is going to be the maximum value. Right? If I do this 1,000 times, I get a sense of if I just randomly threw down where the measured points are, I'm still going to find some maximum range. So I want to know, did what I find, is that larger than random? This is how I get rid of the multiple hypothesis testing issue. Otherwise, it's hard to know what is actually significant. There might be other ways around this, but this is standardly what's done.
Excuse me. Something I'm not following. What is the probability taken over?
There's no probability yet.
Is that a probability?
Oh, this. Let's not worry too much about this. This is assumed that the measured data comes from a Poisson distribution, or something. You put some model on the data. Right now, otherwise there's no probability. This is just some model, some function I'll optimize. Maybe I'll explain now. I'll come back to it. But otherwise, there's no real probability in what I've. Just think of this as some function. Okay. Okay, so and this is used like widely in geographic information systems. There's a 538 article that talked about this algorithm. Okay, so this is used widely in geographic analysis to detect outbreaks of diseases and so forth. The typical algorithm that's used and the software that's used is by Kulldorff, and is basically the same software I think he wrote 20 years ago, and it runs like this, and this is in, I think, seconds on the left-hand side. We can run it up to maybe 3,000 points before it starts taking kind of hours. Okay, and so if you have much bigger than 3,000 points, you're in trouble. But keep that 3,000 in mind. That means if we're going to run what they're doing, our core set cannot be bigger than, say, 3,000, right? Or we run into trouble. Okay, so we really need to get a really small size core set here. When I was in grad school, more than a decade ago, I improved this a little bit. I was very, very proud of it, but it really doesn't address the big data issue. Okay. Okay, so what we're going to talk about, this is a popular heuristic that I have the binary for, but otherwise I don't think people use this in practice. We have a new algorithm that even beats this heuristic algorithm, and then we'll actually improve upon this. Okay. So and with guarantees. Okay. Okay. So back to this statistic function. The way to think about this is if I look in a particular, I fix one cluster or one range here. I look at the fraction of the baseline points in the range and the fraction of the measured points in the range. Okay, and I want to basically the function might as well be the absolute value of the differences of these fractions of the points. Okay, this is not what's used in the statistical setting. They usually use what's called the Kulldorff scan statistic, or there are other variants of this, which is a more complex function of these fractions. But in general, what we've shown in various ways is that you can approximate this by a bunch of the upper envelope of a bunch of these piecewise linear functions. Okay, and so each of these basically looks like this. Okay, and how many do I need to epsilon approximate this? We recently reduced the number from basically 1 over epsilon to 1 over square root epsilon. So it's, and in practice, it's like 3. Okay, in practice, we need 3 of these linear functions to get pretty good approximations on real data. So we can think of just this function, and if you think the measured and the baseline points have roughly the same number, then you can think of just the point that's the red points and blue points, and the range that has the biggest difference between red points and blue points. This is essentially the same problem. Okay, and this shows up like the maximum disagreement problem in old machine learning kind of nomenclature as well. Okay. Okay, so we need to now scan every range, just give you a sense of what this is like for disks. Now we want to think of every possible range, but using geometry combinatorially, we know that every disk is defined by at most 3 points. I can shrink it until it can't shrink anymore, and there'll be at most 3 points which are needed to define this region. And it turns out, so I could kind of iterate over all these. I can actually do this efficiently without having to recompute the sum. I pick every pair of possible points, and then I can kind of sweep through some order defined by this pair. And so this takes n cubed time for all n squared pairs, and then a linear time sweep. Okay, so I can basically do this in n cubed time for disks, and similar things for half spaces, it's n to the d. For axis line rectangles, it's n to the 2D. Disks are actually, there's actually a log factor in this algorithm if you're not careful, but you can reduce it to half spaces 1 dimension higher, and you can get the result for half spaces. And this is like an old SOTA 93 paper that shows how to do this. Okay. Okay, so these are polynomial time algorithms. For low dimensions, they're not too bad. And this is really the big computational problem we need to solve. Okay, So, and this is more general than just these sets. We define this notion called a conforming range space. This range space, this idea is like a function space in machine learning, but we'll think about this geometrically. And I want to have things that have a notion where I can do something like take all the points, take it and shrink the disk until it hits the points. And I generalize this called conforming range space, where I need two properties. One is that I can define some essentially smallest enclosing disk sort of function, and then if I ask what points are in the smallest enclosing disk, it should be the same points as before, right? So I need some function like that, which is usually pretty easy to do in a lot of cases, and I need something that if I pick a subset of points, which is not necessarily one of the valid ranges, and I find the smallest enclosing disk and I look at that range, this needs to be a valid range as well. It's different. It now has this other blue point, but this is still a valid range in my class. This is not always true. For instance, if I looked at something like smallest enclosing triangle instead, I could start with this point, and the smallest enclosing triangle might look kind of structurally somewhat different, and then I don't recover the original point set. And so I don't always get this property, but I think this is still fairly general.
So again, I mean, from the point of view of the machine learning, computational machine learning, it looks very much like compression scheme, sample compression scheme. You want to pick a few points from the sample to recover the hypothesis that behaves on the sample similarly to the one that you started.
Yeah, so I mean, it's possible. I think the first part will definitely be known in machine learning. It's not the main result. Second part, maybe it's known. We weren't aware of it, and then there are improvements on that I'm confident were not known before. But still, these are all polynomial runtimes. They still look like this. Okay, so we want to create a Coreset. And so the typical Coresets for these things in geometry, they're called epsilon samples and epsilon nets, right? These were developed between geometers and machine learners like Vapnik and Cherveninkas and Hausler and Welzo a long time ago. If they have something called the VC dimension, it describes the combinatorial complexity of these ranges. Okay, and so then if you have an epsilon sample, it guarantees that for any, it's a subset of the points, S, such that for any range in this class, that you guarantee the density, the fraction of points in this range is off by at most epsilon, right? So in this case, there are 22% of all points and 25% of the red points, and that difference is kind of your epsilons and typically added to var. Okay, they're somewhat relative versions, and those don't seem to make a difference in what we're doing. Okay, and there's also a concept called epsilon net, which is just that for any large enough range that contains enough of the data points, you'll hit that with somewhere in your sample. Okay, these are similar to classic learning, basically same as learning complexity notions. And 1 over epsilon squared points basically gives you an epsilon sample. 1 over epsilon log, 1 over epsilon random sample points gives you an epsilon net. Okay, so the epsilon net is a weaker notion, and you need fewer points. Okay, but epsilon sample seems like what we need. So idea is you do sample this, and also for the red points, the measured points independently, and then you scan over this. Because you approximate this, you can show you basically approximate this function. Okay, you can, in this general conforming range space model, you can get runtimes like this. And to these special cases, you get things like 1 over epsilon to the 6 for disks. Okay, it's better for half spaces and rectangles. We can do 1 over epsilon to the 4/5 with some other tricks in there. These are still too slow. We basically need epsilon to be like 0.01, and then S squared, S is like 10,000, and S squared is like 100 million, and this is basically the runtime, and this is too slow. That's for, I guess, for half spaces. For disk, it's worse, right? So this basic approach doesn't work. Okay, so a simple idea is let's try and use nets as well. Okay, so basically I'm going to now take 2 subsamples, and this is the main idea that gives us the biggest improvement. We take an epsilon sample, and this will approximate our counting properties, but we need a net here. I'll describe exactly what the net is after I describe with this result. We're going to use the net to induce a range space. And this is a little tricky, and you need to go through these kind of conforming definitions to make sure this works. And in a way where I'm going to only consider the ranges defined by the conforming kind of map onto the geometry defined by the net points, which is going to be much smaller than the epsilon sample, right? And then I need to map this back to the full data set, right? So I need to define a range on the points in X only defined by the ranges described by the points in the net. Okay, and this is, if you can parse through that set theoretic definition, that's what this is saying. And it has the property that if you do this correctly, that for every range in the full space, for every range I consider, I can evaluate it on the sample, right? This, not the full set, but the sample. One of the ranges in the net is going to be close by in the counts, which is going to apply as close by in the function we're trying to optimize as well. Okay? And so in order for this to work, the net is not on the original space. It's actually on what's called the dual range space, which I won't get into. But if you do this, then you get sufficient covering of the space of the ranges that you want. And you can get this property, and this works.
So you get some factor of 2.
What?
You get some factor of 2 when you go from one to the other.
Between the dual and the... I mean, worst case, it's an exponential factor. But in these cases, it's all small. Sometimes it's better in case of disks, actually, I think. Okay, yeah. And so this drives these runtimes down. There's a general result for disk. It's now 1 over epsilon to the 4th. For Halfspace, it's 1 over epsilon 3rd. It's these are significantly smaller. And it turns out that this is how we get this bound here, which is much faster, along with some careful implementation of scanning. Okay, so this is kind of the main conceptual idea of how these Coresets can allow you to get practical algorithms on this big scanning technique. If we didn't get the right size Coreset with using the nets, then this runtimes are just too big. We basically need the net to be the size about 100, and the sample can be in the size about 2,000, and that's still okay to get really fast runtimes. Okay, I should mention that we're no longer finding the exact best range anymore. We're finding an approximately best range. So we should check that this actually still works. We can approximate the function, and from a theory point of view, this is initially all I checked, but then, talking to statisticians, like, well, is this still statistically powerful? And the idea is, if you plant a region that you know in there, so I choose some disk, I put more measured points inside the disk than I do outside, am I able to find the disk still, even with this approximation, right? So these plots before were tuned so that we found it, but just to kind of explain what this is, we do this and we repeat it many times. What fraction of the times are we actually recovering the disk? This is the statistical power of this algorithm. And from a conversation with Ari, explaining with some of his papers, they showed that actually scan statistics are in general like very powerful in doing this, the right way from a power perspective to do this. And so one issue with measuring this is, even if you plant a region, the region you find might not be the planted region. Because I planted this, but it wasn't, the region I found did not go all the way out to the boundary. So there's like various tricky things in how you actually evaluate whether you actually recovered the right region, but small Jacquard distance seems reasonable. And we can show that if we set basically the size of the net to 100 is pretty safe, but it can go lower, you get pretty high power. Or if you set the size of the sample to maybe 3,000, or I guess 2,000 isn't doing too well in this example here, but with 3,000 I'm getting pretty high power. Right, so if I set these large enough, I can get pretty high power, and these are the runtimes at this scale with some other with fast implementation tricks, I was able to get this plot here, where this is much, much faster. This runs in fractions of a second. Okay. Okay, so can we do better here? I just used random sampling. It's known in the Coreset literature that these corsets have been studied, and you can actually do better than random sampling in the sizes here. But to do that, I need to be careful about a couple things, like can I get a smaller corset in place of here, either for the net or for the sample? And it turns out in both cases it's going to be yes. The random sampling adds like log factors or even polynomial factors in the size of both of these. But to do that, I need to, like, these are known, and some of these were for a long time only known existentially. I need to be able to compute this fast. Right? A lot of the Coreset and sketching literature works because I can compute these things in basically near linear time on the full data set size. Otherwise, it doesn't make sense. So as I mentioned, some of the best algorithms were actually large polynomials in the size themselves. So those, it seems like I might be able to do better with this. It was not obvious how to do that. We need to invent new ideas here. And actually, another thing we realized is that once we have approximated the data, we actually don't need to scan things exactly. You can actually get more improvement if you approximate actually the scanning process itself, even on top of the approximate kind of space of ranges that you're dealing with. And this can also save you more polynomial factors in various things. So there are a number of subtle improvements using geometry that we've been working on over the years. I'm not going to describe all of those to you, but I'll highlight a few things. Okay, and maybe that might be a little bit of more general interest. Okay, so this is for the rectangles problem, the scanning rectangles, and so this green curve is just doing one sample and then running essentially a version, our better implementation of the original StatScan algorithm. Right, so what I'm trying to do is I'm trying to get low error as my time is increasing. And even if I run time for, I mean, this is only 0.3 seconds, but it kind of stays pretty flat. It really have to go pretty far out in time for the error to drop down to something small here. This is the generic two-level sampling I told you about before. And then this is a faster algorithm. So it's really decreasing. I said I wanted to get it about 0.01 error, and it gets here in 0.2 seconds. Okay, this is basically independent. This is on, I think we start with 10 million points. We ran them through a random sample to prune them first, and then we refine that sample, right? So basically arbitrarily large data sets. This is an algorithm that has faster runtime. We basically have 1 over epsilon squared log 1 over epsilon. And we can prove that this is basically, the 1 over epsilon squared is needed here. Okay. Or it's based on a conditional lower bound. Okay, this is a little bit messier. This is for half spaces. Okay, so the two-level sampling is here, 1 over epsilon to the third, and that's the gray line here. This is kind of messier. And we have another algorithm. We have 2 provable improvements on this. One, this is, I think, within 1 over epsilon to the 1/3 of optimal. And these are messy, and this is not going to go into the details of these. But we have another algorithm which is really super simple. And if you kind of just look at these two, after you run long enough, the asymptotics difference kicks in, and you actually get a big drop in the error here. So even though this is messy, you can see over the RAM sampling, you're actually getting a pretty big improvement. And this, in practice, this really plays out. This plot's not the best at showing this, probably. Okay, so I will, yes, that's right. So I'll try and kind of explain in the last 10 minutes or so kind of a couple of where these improvements come from. Okay. So if we think about this again, I've got basically 3 steps in my algorithm. I create the epsilon sample, I create the epsilon net, and then I scan over this, or approximately scan, as we'll see, over this restricted set of ranges, evaluating them on the sample. Okay. Okay, so the story for half spaces, where the biggest improvement here is coming from, is that it's known that there exist epsilon samples of size, this is in the plane, 1 over epsilon to the 4/3 instead of 1 over epsilon squared. And we're able to basically construct these within a log factor in near linear time. This goes from 1 over epsilon to the 3rd to 1 over epsilon to the 7/3, right? This is 1 over epsilon 2.33, right? For axis line rectangles, the big trick is to approximately scan instead of scanning over these ranges exactly. And so we're able to scan in basically n squared plus s running time. And basically you can do these all with just random samples is how the fastest, best construction of the samples in the nets. And this goes to basically 1 over epsilon squared. And there's a conditional lower bound that this is optimal. Although an algorithm which is n cubed is less complicated, and I'll explain that. And that one's the one that's super fast in practice. That's still an improvement over this 2-level scanning with just random samples. Okay, so let me mention how we do both of these. Okay, so the existence of these epsilon samples for half spaces was known existentially since the early 90s and known to be tight as the right bound here. But it wasn't known how to actually construct these. These were existential constructions for a long time. There's a sausage paper that dealt with streaming algorithms for these. And it says that the high computational complexity of currently known algorithms for these subroutines may be prohibitive for data stream applications. It's a long thing, open question problem to find efficient, exact, or approximate algorithms for either of them. Okay.
Again, it's not clear to me what do you mean by non-constructive, because those results that the Welsel and Hausler show that if you just randomly pick a sample of that size, you are high likely to get an epsilon approximation.
The Hausler and Welsel was for epsilon nets, right? It's for epsilon samples is what I want to get here, right? And so that was that. Basically, there are these discrepancy-based approaches, and the best bounds here were non-constructive for a long time. So Bansal, this important Fox 2010 paper, which basically made all these things constructive. They'd relied on the pigeonhole principle in the proof. And then there's been some refinement over the year. There's several papers along the lines. I guess Casper Larsen may have and maybe some other authors have some papers that maybe don't use an SDP anymore, but they're still basically, these become like the size of the data times 1 over epsilon to the 4th runtime, which is bigger than what we want. Okay, so they can get these, but the runtime is too big. Yeah.
How do you define an epsilon sample again? Is it a sample such that the fraction of points within your set is epsilon away from the real fraction?
Yes, for every set in the class. Yeah.
But then, as Shai was saying earlier, if the class is VC, then a random sample should...
but that only gives me 1 over epsilon squared, okay. And that size shows up in the runtime. And so that turns out to be the bottleneck in this algorithm. Right, so if I can reduce this, the downstream algorithm will run faster, and this leads to this difference in the plots that I showed you.
So the main thing is that we get here epsilon to the 4 over 3 rather than epsilon to the 2.
Yeah.
Right, and it turns out it's pretty easy to do. This surprised us. That okay, there's a thing construction in geometry known as a TZ partition. Or just a partition. It's defined with respect to range spaces, but you can think of this for half spaces in 2D. And what it is a decomposition of the point set into these cells and these subsets. So each cell contains the subset. The cells may overlap, but the subsets are going to be disjoint. they're all approximately the same size, and the property is that any half-space boundary crosses at most t to the z of these.
Okay. And this is specific for half space or for any small VC class?
I'm not sure if it's every VC class, but it's more general than half spaces. You can define these, I mean, like you can do for disk through lifting, but I think you can, I'm not sure if it's every VC class, but it's more general than half spaces that you can do this. Okay, so yeah.
Your picture, the partition creates the triangles in the picture.
Yeah.
And you're trying to have good properties with respect to all these half spaces.
Yeah. Yeah, and this has been studied. These are very classic results in geometry. Basically, Matuszek kind of basically had a good solution in the early 90s, refined by Chan and about 10 years ago. And basically, you can get a z equals 1/2 partition in close to linear time. Okay, but there are even older results. These kind of came up in data structure literature. These are the core of understanding data structures for half-space queries, basically. And before that, there were older results that had weaker values on z, and I'll get back to these. Okay. Yeah. So actually, I'll tell you right now. These are actually much simpler. These approaches by Matuszek and Chan are pretty complicated. My student actually implemented them. It took him like 9 months to do so, and it could have taken a lot longer. He's pretty. It would have taken me a lot longer than 9 months. They're very complicated. I don't think anyone has their core structure, but I think no one's implemented them before. Okay, but this we realized this afterwards. This structure is much simpler. The bound on z and then the Coreset size isn't as good, but it's simpler. The idea is basically you build a KD tree. So you split vertically and then you split horizontally, except the second split, the horizontal split, has to be a single line. Okay, so I have to have what's called a ham sandwich cut here. So it has roughly half the points on either side, but it's a single line going through. Okay, and you can do this in linear time, or you can sample a couple things and it gives you a good approximation, and then recursively on down. So every recursive split is, with this I can just use median, the second one I do a ham sandwich split. And then this refinement is it's all ham sandwich splits. Okay, and then the partition is just the cells of this. That's it. So I can build this very, very quickly. Okay, now once I have a partition, the new idea is that this gives you an epsilon sample very easily. For each cell in the partition, I choose one point at random. That's it. So now we have a fast construction. The proof is actually is very simple. There's only some number of these cells which are cut, so it's just a Hopting bound, right? There's some number which are cut, which is not too big. Each of them has a small number of things in them. You plug it in here, and you get this. Right. So it's a very, very simple proof.
So you get the optimal epsilon to the 4/3?
Yeah, there's an extra log factor here, which is non-optimal, which is less. It's actually less than 1 log that we're non-optimal by. But it's now near linear time instead of some big polynomial in the size of the set you get, which matters. Okay, so this was a very simple result. Okay, and this, so basically the ham sandwich tree cut is this purple one, which is doing really well. These other cuttings we can actually get to be competitive with the random sampling, which I'm very proud of, but it's not actually proving much in this result. And I think I'm out of time, so I'll skip the rectangle scanning, but this you can do faster by, you define an adaptive grid, and then you just need to solve something nearby in the grid. This is where the approximation comes in. And then you can scan it this is the 1/epsilon to the 3rd time, because in every strip here, you can do this in linear time, and this with some trick here. Okay, and this gets that gets this improvement down here. Okay, so faster scanning makes a big difference in the rectangles. Okay, but I think I'm out of time, so I'll end here and say a lot of this work was my student Michael Martini who implemented and came up with kind of the core of most of the proofs. The rectangles is conditionally tight reduced to all pairs shortest path. There's an iCalc paper which basically showed that for the exact case a few years ago. We think the half spaces we can get to this, although we've alternated between thinking that this was the right bound as well. Or maybe, I think we had a conjecture that was like 1/9 less than that. It was like, and that's 1 over epsilon to 1/9 less than that. But and all the codes is also on GitHub. Okay, so I'll stop here.